So we're in this section on curve sketching, which isn't really anything new. We're really pulling together things that we know from pre-calculus and then combining that with our new information we can get from first and second derivative, and then just kind of pulling all that together to look at sketches of graphs. Like for example, this last one that we did, and you can kind of see where we ended last time up here looking at this graph. So let's take a look at another example. Number 2 is 7e to the 7x times 2 minus x. And so we are going to, again, essentially find first derivative information, second derivative information. But before we do that, let's start with just identifying some of those pre-calculus facts, I guess I would say. Things like asymptotes, domains. We always want to think about if we have a restricted domain. And things of that nature. So let's first just kind of recognize here that the exponential function has a domain that's all real numbers, e to the 7x. You can plug in anything for x. And similarly, 2 minus x, there's no issues there. So let's just first start by just acknowledging here that our domain, so the domain on this function is going to be all real numbers. So we're not going to have any kind of restricted domain here to worry about. All right, now in terms of asymptotes, this isn't a rational function in the sense of a polynomial divided by a polynomial, where we already know here there won't be any vertical asymptotes because the domain is all real numbers. So that definitely rules that out. But horizontal asymptotes, we do want to think about the exponential function, e to the x there, or e to the 7x, does have a horizontal asymptote at y equals 0. So we are going to have, so let's write that out as we think about this, kind of pulling it all together and making sense of it eventually when you look at, probably looking at it on your graphing calculator in conjunction with all the information you find by hand. You will see a horizontal asymptote at y equals 0. All right, let's look at the intercepts. So it's always nice maybe just to have, if there's some, a couple points maybe potentially to plot. And so when we think about first, maybe let's look at our y-intercept. And so remember, the y-intercept is where you sub in 0 for x and solve for y. So you're going to have 7e to the 0 times 2 minus 0. Well, e to the 0 is 1. And so we're going to have 7 times 2, which is going to be 14. So we are going to have, there would be a y-intercept then at 0, 14. So that's kind of useful information. Again, just kind of thinking about, pulling this all together and sketching your graph, horizontal asymptote at y equals 0. All right, now X-intercept, or potentially intercepts. There could always be more than one of those. So remember, that's where you sub in 0 for y. So essentially you're setting your entire function here equal to 0. And it is a product already, it's factored, so you can think about setting each factor equal to 0. So that's at least, kind of what you're thinking about here. Now, in the first case, divide by 7, you have e to the 7x equals 0, and hopefully you recall that there's nothing you can raise e to get to 0. If you were to attempt to solve this, maybe by taking the natural log of both sides, because that's how you would solve a exponential equation. This would be your reminder if you were to attempt to do this into your calculator. Of course, this does not exist, so maybe that's where you would stumble into that particular discovery. Hopefully once you've reviewed that, that'll come back quicker every time. Now, on the second one, of course, we can add the x to both sides, and we do get that x is equal to 2. So we do have an x-intercept at 2, 0. So we did have a little bit of pre-calc information here that's useful to think about before we jump into all of the calculus information. All right, so now let's do that though. Let's jump into the calculus information that we can find. So let's go ahead and start with our first derivative. So as we are looking at that g up above there, hopefully you recognize you have a product of two functions of x, so you need your product rule. In terms of the 7, I tend to just sort of lump that with the first function. You could factor it out in front of everything if you prefer, but I'll say that's my first factor. I'll leave that first function alone, times the derivative of the second one, which would just be -1. And then plus we change that order, so the 2 minus x left alone. And then the derivative of 7e to the 7x is 7e to the 7x, but then by chain rule times that 7, that derivative of the inside. All right, so taking a look at this, if we're going to attempt to look for where this is equal to 0 and solve and those sorts of things, we really would like it in a factored form. So as we look at this, hopefully you can kind of observe here that you have a common factor in both terms that you can factor out. So that's what we would like to do here, and in fact what we are going to do. So let's go ahead and factor out this 7e to the 7x. So we are factoring that out from both terms. And that means in our first term we have the -1. In the second term we still have that extra 7 that came from that chain rule. And then of course we also have the 2 minus x binomial. So we now have 7e to the 7x times the quantity of -1 plus 14 minus 7x. So combining your like terms inside of that set of parentheses there, looks like we're going to have -7x plus 13. So 7e to the 7e to the 7x times -7x plus 13, that is our pretty good looking form here for g prime. All right, now we want to take a look at and think about where g prime is going to equal 0, or potentially where g prime does not exist. Now, in this particular situation, we don't have any issues where this function won't exist. E to the x is defined everywhere, obviously, so is that binomial. So nothing to worry about there. The major culprits, of course, are denominators and even index radicals and maybe log functions, but those are the things that kind of restrict our domains and might cause potentially where the derivative could not equal or would not exist. All right, so where is g prime equal to 0? All right, so once again, we already have this factored, so we are setting each factor equal to 0. We've already done this once in considering the domain. There's that same factor again. We don't get any solution from where e to the 7x is equal to 0. But of course, we will get a solution from -7x plus 13, and where that's equal to 0. So simply adding your 7x to the other side, and then just thinking about dividing both sides there by 7, so just dividing both sides by 7. So we are going to get our 13/7 as our critical point, or if you prefer, if you want to think of it as a mixed number for some reason, that's obviously okay as well. So we end up with 1 6/7. Okay, so this is our critical point, and this is potentially a min or a max. So now let's go into our sign analysis. So we want to perform our sign analysis here. And remember, I want to see the labeling. I want to know that you know what you're subbing into. I want to know that you know what conclusions you're making, about what function. So we're subbing into the derivative, making conclusions about the original. And put my critical point there, 13/7. And so we're going to sub in something less than 13/7. So I'm always a fan of 0. Typically, if I can use it, I go with it. So we're subbing 0 into our derivative. Well, 7 times e to the 0 is 1, so that little monomial in front is going to be positive. And then 0 plus 13 is also positive. And a positive times a positive, of course, we're positive. And where the derivative is positive, the original function here is going to be increasing. Something bigger than 13/7, so 14/7, which would be 2. So let's go ahead and just sub in 2. And so, again, 7e to the 14th would still be a positive monomial. And then 7 times -2 would be -14, plus 13 would be negative. Positive times negative is negative, so we are now decreasing. And so that means that at the location of x equals this 13/7, this is going to be the location of a local max. All right, so here's what we now know. Let's even jot the facts off to the side here. So we know from our first derivative, we now know that we are increasing from negative infinity to 13/7 or 1 6/7 if you prefer. And we are decreasing from that, again, 13/7 to infinity. And we now know that we have a local or relative maximum at 13/7. And then remember, whenever you want the y-coordinate, it's always plugging back into the original function, which you can go to your calculator for. Our original function was 7e to the 7 times x, which would be 13/7, and then times, what was that binomial? 2 minus x. So then times 2 minus this 13/7. Okay, so this is going to be 7e to the 13. 14/7 minus 13/7 is actually just going to be 1/7. And so these 7s are going to reduce, and so we are going to end up with just e to the 13th. So the local max, a huge y value, if we were going to kind of take a look at that in our calculators, e raised to the 13th power here is a very large number. So that is everything that we can get from the first derivative. And that's plenty. All right, let's go on now and see what we can find from our second derivative information here. All right, so now we're going on to g double prime. So we're going to be working off of the g prime that's still in the upper right-hand corner up there. Again, product rule. So first one left alone, 7e to the 7x times the derivative of the second factor. Derivative of negative 7x is just going to be negative 7, and of course 13 goes to 0. Plus, change that order, so the negative 7x plus 13 left alone, and then derivative of 7e to the 7x is 7e to the 7x times chain rule, another 7. All right, so once again, similar situation. If we're going to work with this, we really want to be able to have it in a factored form to set it equal to 0. We can also, in this one, factor out, looks like altogether a 49 e to the 7x. So let's do that. And it's kind of up to you, user's choice, if you want to factor out the negative with that first term or not. I didn't highlight it, so I guess I'll just stick with just factoring out the 49 e to the 7x. So that's what got factored out. And now in the first term, I still just have this negative 1. And then in the second term, I have this negative 7x plus 13. And so combining my like terms, we're going to end up with a negative 7x plus 12 in parentheses there. All right, so this is, again, actually the algebra in this one's easier than our first example we did. And so we have it in a nice factored form. So once again, we're going to look for now where the second derivative is equal to 0. And then, of course, just kind of considering where the second derivative potentially might not exist. But, of course, we don't have anything for this one. All right, where my second derivative is equal to 0, once again, considering where the first factor would go to 0, of course, gives us nothing in this case. And just, you know, the solving actually on these hasn't been too bad. We just have a nice little monomial here that we're setting equal to 0. I'm sorry, binomial, we're setting equal to 0. And so adding the 7x and then just dividing both sides by our 7, we are going to get that x is going to be 12/7, or if you prefer, 1 5/7. That sometimes is helpful just to think about it that way as you're doing your sign analysis. But so let's go ahead and do that sign analysis. All right, so let's take our, now subbing into labeling my second derivative so that I can make conclusions about the original. And again, I'm using my 12/7 in this case on my number line from where the second derivative was equal to 0. And so picking something less than 12/7, this is going to feel a lot like what we did on the first derivative. I'm going to just go with 0. The monomial, e to the 0 is positive. 0 plus 12 is positive, and so we are positive. Now, positive in the second derivative means the original function is going to be concave up. And then plugging in something bigger than our 12/7, so again 14/7 or 2 would once again do the trick. So let's sub in 2. And so still positive on that monomial. Negative 14 plus 2 would be negative in the binomial. Positive times negative is negative, and we are now concave down. And so here at x equals this 1 5/7, we are going to have an inflection point there. So if we wanted to kind of summarize our information here off to the side, let's go ahead and write this out. Oops. All right, so we are going to be concave up on the interval from negative infinity to 12/7 or 1 5/7. We are going to be concave down from that 1 5/7 to infinity. And we did find ourselves with an inflection point here at 12/7. And then again, subbing this back into the original function. So my g of 12/7 is 7e to the 7 times this 12/7. So those 7s would reduce, times 2 minus this 12/7. And so 14/7 minus 12/7, this whole thing here, this would be 2/7. Those 7s would reduce. And so we would end up with e to the 12th and then this extra factor of 2 here. So we're going to end up with 2e to the 12th. So those are the key facts listed out that we get from our second derivative. And then I think I'm going to just erase a little bit of this in here because I'd like to put in a sketch of the graph in this lower right-hand corner. So I'm just going to create a little room here. And so as we pull all this information together, we could also take a look at our graphing calculator. This might be a nice time to do that. So I've already entered in our function into the y1. And right now, if I'm just in my typical Zoom standard, so Zoom 6, you know, because that max, if we were to look at the location of that max was like e to the 13th, I think it was, we're going to be way off. I mean, if I increase the y max so we could actually get to the max at the top, it's just going to be like this straight up and straight down almost. So I'm not going to really adjust my window and try to get that to fit. We already kind of know where that value is. If we went back and took a look at, I'm going to scroll back up here. I'm going to slide this over to the other side. Yeah, e to the 13th. So if I go back to my main menu here real quick on my calculator and I do e to the 13th, that max value is way up at 442,000. And if I look at like where the inflection point is, so 2e to the 12th, that's going to be at 325,000. So attempting to get those to fit would be, you know, pretty difficult, right? So I don't think I'm going to really worry so much about that. So let's just take a look at maybe, just move this out of the way, maybe, or not. Okay, just a second. There, that'll work. I just wanted to get rid of that graph. Okay, so let's go ahead and take a look at, we'll just do a quick, to end this here, we'll just take a quick rough sketch here of our graph just to kind of identify the key features here. All right, so maybe the one thing just to kind of identify is we did have a horizontal asymptote that was at y equals 0. And then our graph, if we were to graph this here, you know, so it's obviously approaching, and it almost looked like it was so flat there, but it is approaching that horizontal asymptote. And then let me see, where were our, scroll back up here, 0, 14 was the y-intercept. So as this is not going to be drawn to scale, but as this gets, as a matter of fact, let's go try this again. So we are going to cross, I'll say that this is at my 0, 14. And then when this goes up and comes back down, extend this on the other side, it's going to cross at 2. So this one's awfully hard. I maybe should have just had us end this whole thing by just looking at what it was going to look like on the graphing calculator. But it's going to come up and then it's going to eventually, you know, come back down. It's very, very steep here. Wow, this is so not drawn to scale. So this is crossing. I'm just going to label it though. This is crossing here. This was at 2. So we had an x-intercept at 2, 0, a y-intercept at 0, 14. And then at 1 5/7, so like wherever it changes, so it starts off concave up, and then it changes to concave down, we could say that this is at 2e to the 12th, and you know, this value right here then would have been at the 12/7. And then it goes all the way up and it hits that max up here. I extended this. And so this max was at this e to the 13th. That was the max value that it hit. And that max value occurred here at 13/7. So that happened at 13/7. So awfully hard to try to get this one to fit in. But in any case, the information does come together. When you look at your graphing calculator and you look at what you find, the information comes together. That's the key that you want to make sure you're kind of always checking.